Put the heading Chapter 4 Combination Circuits. First topic, block diagram of combination circuit. First draw the block diagram of combination circuit. Here, if you are having single input, that means single bit you are having. Okay, we can represent that particular bit with either 0 or 1. That means two combinations you are having at the input side. Okay, and those combinations will affect the output. Similarly, if you are having two inputs, then you can represent four combinations of zeros and ones. 0, 0, 0, 1, 1, 0, 1, 1. Okay, each combination of input will affect the output. Okay, like that, if there are n inputs, then there will be 2 power n combinations of zeros and ones, and each combination of the input will affect the output. Here the output purely depend on the combination of present inputs. Hence we are calling this particular circuit as combination circuit. You can write down. Combination circuit is a digital circuit whose outputs depend purely on the combination of present inputs. Next point, if there are n inputs, then there will be 2 power n combinations of zeros and ones. If there are n inputs, then there will be 2 power n combinations of zeros and ones. Each combination of zeros and ones will affect the output. So internally you will be having logic gates. Okay, when we see whatever the simplified function we got, that function we have to implement with the help of logic gates. So internally combination circuit will have logic gates. Next point you can write down. Logic gates are the basic building blocks of combinational circuits. Okay, you can write down examples of combination circuits. Binary adders, binary subtractors, magnitude comparator, decoders, encoders, demux, mux. Next point you can write down. Combination circuits do not have any feedback path, because here outputs purely depend on the combination of present inputs. Okay, here we don't have any feedback path. First let us start with binary adders. As the name implies, which performs the addition of two binary numbers. Right? Binary adder means it performs addition of two binary numbers. For the time being, let us start with two single bits. I am considering A and B are of two single bits. Okay, so here you can represent four combinations of zeros and ones. We want to perform the addition of these two single bits and we'll write the corresponding sum. Okay, we want to add these two bits. Okay, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2. We cannot represent 2 with a single bit. Just like in our decimal number system, okay, whenever you are adding two decimal digits, if the resultant sum is less than or equal to 9, we can represent with a single digit. When sum exceeds 9, we require one more digit, that is called carry. Similarly here, in binary, if you are having a single bit, the max value you can represent is 1. Okay, when we are adding two single bits, if the resultant sum is less than or equal to 1, we can represent with a single bit. Okay, now sum is exceeding 1. Okay, that means we require one more digit, that is nothing but carry. 2 is the decimal number, we can represent in binary as 1, 0. That means here 0 is the sum, 1 is the carry. Right? So here I will consider one more bit, that is carry. In previous three combinations we don't have any carry, so I am placing simply 0. Here we are considering the addition of two single bits. Okay, first three cases the resultant sum is less than or equal to 1, so I require one bit is sufficient. Okay, whereas for last combination I am getting sum as 2. 2 we cannot represent with a single bit, so we require one more digit, that is nothing but carry. Here carry is 1, sum is 0. Now just observe one particular output with respect to input. Okay, just close this one. What is this particular truth table? Just observe inputs AB and carry C and get, right? So we can directly write C equal to A and B. Now similarly you close this column, just observe the inputs and S column. What is this one? Exclusive OR, right? S equal to A exclusive OR B. C equal to A and B, S equal to A exclusive OR B. Now we got the logic expressions. Next step is we have to implement these expressions with the help of logic gates. We require a 2 input AND gate, a 2 input XOR gate. A and B are the inputs, carry is A and B, sum is S equal to A exclusive OR. Just look at this dotted line. Okay, consider this is like block diagram. Okay, here we are having two inputs A and B, and it is producing two outputs C and S. Okay, outputs purely depend on the combination of present inputs, right? So hence this one is the example of combination circuit. Okay, inside this combination circuit you are having logic gates. Here I am having AND gate, here I am having exclusive OR gate. You can make a note. Half adder performs the addition of two single bits A and B and produces two outputs, carry C and sum S. Okay, here we have considered for the addition of two single bits. In general, we will be having multiple bits. Okay, for the time being, let us consider for 4-bit case. A is 4-bit number, A3, A2, A1, A0. Similarly, B is another 4-bit number. Okay, I am considering A and B are two 4-bit numbers. Okay, we'll start the addition of these two numbers from the LSB side. Right? First we'll add these two bits. Okay, and we'll place the sum here. If carry comes, carry will be added here. And we'll add these 3 bits and we'll place the sum here. And if carry comes, carry will be added here. Like that we'll continue the process. So here if you observe, whatever the adder which we have discussed. Okay, here I am having 2 inputs and 2 outputs. This particular adder I can use for adding A0 and B0. Here I am having 2 inputs A0, B0 and 2 outputs S0 and C1. Okay. Whereas if you observe these 3 bit positions, I am having 3 inputs, among which 2 are the inputs corresponding to A and B, and third input is the carry from the previous stage. Okay. If I want to perform direct addition of these 3 bits, this particular adder is not sufficient. Right? So now let us implement one more adder which performs the addition of 3 bits. Okay. So now another adder is full adder. Inputs are A, B, C in. C in is the carry from the previous stage. And what we are getting when we are adding 3 bits, we are getting sum and carry, right? So carry I am representing as C out, sum as sum, SCM. Okay, previously I have considered C and S. Just in order to distinguish, here I am using different labels. C out for carry, sum for sum. Okay, here I am having 3 inputs. Total you will be having 8 combinations of zeros and ones. Write all those 8 combinations. These are the 8 combinations of zeros and ones. Okay. Here we are performing the addition of 3 single bits. Right. We have to add all those 3 bits and we have to place the respective equivalent binary number. See, you can consider the previous case also. Here we are adding 2 bits. Okay, that is same as just count the number of ones and place the equivalent value in binary. Here number of ones is 0. 0 we can write it as 0, 0. Next, here number of ones is 1, that is nothing but 0, 1. Here also the same case. Here number of ones is 2, its equivalent binary is 1, 0. Like that, here also we are performing the addition of 3 bits, that is same as just count the number of ones and place the equivalent binary number. Okay, here number of ones is 0, so equivalent binary is 0, 0. Next, number of ones is 1, so 0, 1. Here also 1, 0, 1. Here number of ones is 2. 2 is nothing but 1, 0. Here 1, 0, 1. Here number of ones is 2, 1, 0. Here also number of ones is 2, 1, 0. Here number of ones is 3. 3 we can write in binary as 1, 1. Just count the number of ones and place the equivalent binary number. That is same as adding 3 bits. Both are same. Now just observe the inputs and observe the sum column. Observe the inputs and sum column. How we can write sum expression? See here, number of ones is 1. Here number of ones is 1. Here also 1. Here 3. Number of ones is 3. For those combination of inputs, I am getting sum output as 1. Yeah, exclusive OR gate, right? Sum equal to A exclusive OR, B exclusive OR, C in. When you are having odd number of ones at the input, okay, if you are getting output as 1, that is nothing but exclusive OR. So we can directly write sum equal to A XOR B XOR C in. Now let us write the expression for C out. C out is getting 1 for these 2 combination of inputs and for these 2 combination of inputs. Okay. Now let us write the min terms. C out equal to is getting 1 for this term. Okay. In terms of ABC, how we can write? A bar B C in A value is 0. That means A bar, B value is 1, C in value is 1. B and C in. Okay, plus A, B bar, C in. I have written these two terms. Now, I am writing these two terms. A, B, C in bar plus A, B, C in. In these two terms, we can take C in as common. If you take C in as common, here I am getting A bar B plus A B bar. That is nothing but what? A exclusive or B. A XOR B and C in. Plus, in these two terms, I will take AB as common. If you take AB as common, then C in bar plus C in will be 1. If you take AB as common, here we are getting C in bar plus C in, that value is 1. Okay, so for sum we got this expression, for carry out, C out, we got this expression. See, we can implement this particular expression with the help of 3 input exclusive OR gate, but here if you observe, A XOR B I am using as input, okay, for one particular AND gate, right? So instead of directly implementing 3 input XOR gate, what we can do, first we can implement A XOR B first, okay, and then with the help of one more XOR, we can get overall expression, okay. So that A exclusive OR B, here I will use one of the input for AND gate, other input is C in. Similarly, one more AND gate is there, their inputs are A and B. These two AND gate outputs I will pass through OR gate. Here I am getting A XOR B up to here, but I require in exclusive OR with C in. So I will use one more exclusive OR gate. Now here I am having A and B. So I will use one AND gate. Inputs are A and B. Next, I require one more AND gate. Here inputs are A XOR B and C in. A XOR B I am getting here. C in I am getting here. Just observe. A and B I am getting output of this particular AND gate. This particular term I am getting at the output of this AND gate. Now this is like x1, this is like x2. x1 plus x2. So I require OR gate. This is the circuit diagram of full adder. Here we are having exclusive OR gate, AND gate, XOR gate, AND gate, OR gate. Just observe this dotted line. What is this circuit? Half adder, right? Actually, for implementing this particular adder, here we are having 3 inputs. Okay, this particular adder performs addition of 3 single bits and produces 2 outputs. Okay, for implementing this particular adder, we require 2 adders are of previous type. Okay, hence we are calling this particular adder as full adder and previous adder as half adder. See, for implementing this one, we require 2 adders are of previous type. 2 into half is nothing but 1. Write down. Full adder performs the addition of 3 single bits A, B and C in and produces 2 outputs C out and sum. And produces 2 outputs C out and sum. See, here I am repeating once again. See, whatever the, okay. See here, just observe, for some expression I am having A XOR B XOR C in, right? If you observe C out expression, I am having A XOR B and C in plus A and B. Okay, if you observe in these two expressions, A XOR B is common, right? So instead of directly implementing by using a 3 input XOR gate, what I am doing, first I am implementing A XOR B with the help of one exclusive OR gate. Okay, so that output I am giving as input for one more exclusive OR gate. Other input is C in. So here I am getting sum as A XOR B exclusive OR C in. Okay, now observe carry out expression. Here I am having A and B. Okay, so I am using one AND gate. Here inputs are A and B. Okay, so here I got A and B. Here we are having one more product term. Product term is we require AND gate. Okay, for this inputs are A XOR B. One input is A XOR B. Other input is C in. Other input is C in. Okay, so this term we got here. Okay, AB I got here. These two terms I have to give as input for OR gate. Okay, so if you look at this particular dotted lines, this one also, this is nothing but one half adder. Previously we have considered this one also half adder. So that means for implementing a full adder, we require 2 half adders. You can make a note. For implementing a full adder, we require 2 half adders and an OR gate. So that means half adder means it performs addition of 2 single bits. Okay, whereas full adder means it performs addition of 3 single bits. Okay, it doesn't mean half adder means it performs addition of 2 half bits. It's not like that. Okay, for implementing a full adder, we require 2 adders are of previous type. Hence, we are calling the previous adder as half. 2 into half is nothing but full, like that. So accordingly, the names came half adder, full adder. In full adder, if you are making C in value is 0, what is the output you are getting? Just either in expressions you can substitute C in value is 0. What is the sum expression? What is the C out expression? Just substitute C in value is 0. Yeah, carry is C out is AB, AX or B. If you put C in value 0, then you will get AX or B. So that means what? The moment you are keeping C in value is 0, your full adder becomes half adder. Previously we got for half adder, sum is AX or B, carry expression is AB. Right? You can make a note. If C in equal to 0, then full adder becomes half adder. Next one, 4-bit binary adder. Here I have considered A is 4-bit number, B is 4-bit number. Okay, write down this example. I have performed the addition of two 4-bit numbers. Here I am getting resultant sum 5 bits, at most 5 bits. So that means when we are adding two 4-bit numbers, the resultant sum can have at most 5 bits. Okay, so regarding the addition of the least significant bits A0 and B0, we require half adder. So for performing addition of these two bits, I require half adder. For performing addition at these 3 bit positions, we require 3 full adders. If I want to perform direct addition, there is a limitation with half adder. That's why I went for full adder. Full adder performs addition of 3 single bits and produces 2 outputs. Okay, you can make a note. For implementing a 4-bit binary adder, we require 3 full adders and 1 half adder. Full stop. For uniformity, we will use 4 full adders. I will mention why I am using in the place of half adder, full adder. I will mention the reason little later. Actually, for implementing a 4-bit binary adder, we require 3 full adders and 1 half adder. For uniformity, uniformity means all adders will be of same type. Okay. For uniformity, I am considering here also in the place of half adder, full adder. Okay, I will mention the reason why I am using full adder here little later. Okay, for uniformity we will use 4 full adders. Here I am using 4 full adders. Okay, here inputs are what? A3, B3, A2, B2, A1, B1, A0, B0 regarding A and B. Okay, so I will place the similarly respect to inputs A3, B3, A2, B2, A1, B1 and A0, B0. These are the 2 parallel inputs corresponding to A and B for each full adder. Okay, now for first stage full adder, here there is no initial carry, right? So here I am placing C in equal to 0. If C in equal to 0, then full adder becomes half adder. Okay, so here I am getting sum S0 and carry as C1. The carry output of this one is C1. Okay, that one I have to perform addition with these 2 bits A1, B1. So I will give the carry output of this stage as carry input for this. Okay, so here this particular full adder performs addition of these 3 bits and will produce output as S1 and carry as C2. Okay, similarly here the carry output of this full adder will give as carry input for this full adder like that. In this way continue the process. This is the block diagram of 4-bit binary adder. Here we have cascaded 4 full adders. Cascading means what? Output of one state we are giving as input for some other state. That is called cascading. Okay. So here if you observe, for each particular full adder, we are giving the 2 inputs corresponding to A and B parallelly. Right? So hence we can call this particular adder as 4-bit parallel binary adder. 4-bit parallel binary adder. Since we are giving the inputs corresponding to A and B to each full adder in parallel, hence we can call this particular adder as 4-bit parallel binary adder. 4-bit parallel binary adder. Yeah, Cin is will be 0. Here, whenever we are performing addition of 2 4-bit numbers, initial stage you won't get any carry, right? So here carry in is 0. Next, here if you observe, this particular full adder performs addition of these 2 bits, okay, and will produce sum and carry. Okay, this particular full adder has to wait till this carry come. Okay, then it will produce this sum and carry like that. Similarly, this particular full adder has to wait. If this particular full adder is generating carry, okay, then this particular full adder has to wait till this carry come. Okay, similarly this particular full adder has to wait till this carry come. So that means what is happening here? The carry output of this one we are giving as carry input for next stage. Okay, and So whenever here carry is coming, okay, so this particular full adder has to wait till that carry come, okay. Then only whatever the operation, some output we are getting, that will be valid. Otherwise, it may be valid or may not be valid. Because here if you observe, inside full adder, we are having two exclusive OR gates, two AND gates and OR gate, okay. So whatever the circuit diagram earlier we have seen, the same circuit diagram will be there for each full adder, okay. But, so that means the moment you give the inputs corresponding A and B, okay, you will get some output here. But whatever the output we are getting, that may be valid or may not be valid. Because see, if this particular full adder is generating carry, okay, then this particular full adder has to wait till this carry come. Okay, so that means this carry has to consider. Okay, then only here it will be valid, like that. Okay, so here if you observe, the carry propagation is taking place like this, right? The carry output of this one we are giving as carry input for this, and similarly the carry output of this one carry input for like this full adder, like that. So this particular phenomena is called ripple phenomena. See, when you drop a stone in the water, what will happen? The waves will distribute, right? Similarly here, what is happening? The carry propagation is taking place like this, right? So hence we can call this one as 4-bit ripple carry adder. 4-bit ripple carry adder. Yeah, if carry generation is not taking place, suppose see, inside full adder, you are having whatever the circuit diagram earlier we have seen, exclusive OR gates, AND gates, OR gates, okay. So ideally there won't be any propagation delay, but practically there will be delay, right? So the moment you give the inputs A0, B0, A1, B1, A2, B2, A3, B3, in order to get some, okay, whatever the time here it will take, the same amount of time here also, here also, here also. Similarly, for producing carry, when carry input to each full adder is 0. See, for this particular full adder, carry input is 0. If for all these full adders also, if the carry input is 0, okay, that means what? Then the moment you are giving the inputs of A and B, you will get some output after some time, and similarly carry output also, right? So here if you observe, whatever the amount of time it is taking for producing this particular sum bit, here also it is same for S1, similarly for S2, similarly for S3, because whatever the circuit we are having, two exclusive OR gates, the same path is there, okay. Similarly for carry also, okay. So when the carry input for each full adder is 0, this particular full adder is exactly same as that of here, right? Because here also Cn is 0, here also Cn is 0, here also Cn is 0. Okay, the moment you are giving the inputs of A and B, okay, for producing sum, each sum bit will take the same amount of time. Similarly, each carry bit will take the same amount of time. Okay, so but see, there are two cases. One is best case, another one is worst case. You are giving the inputs A and B parallelly. So whatever the case I have considered, just like your first stage full adder, there is no initial carry, right? Similarly, if C1, C2, C3 also zeros, okay, the moment you are giving the AB inputs to each full adder, okay, all these sum bits are getting at the same time. Similarly, all these carries also getting at the same time. Okay, so whatever among these two, whichever is the greater, okay, suppose sum is taking say 40 nanoseconds and carry is getting say 20 nanoseconds, example. So among these two, whichever is the larger, that is say 40 nanoseconds, the same amount of time is required for performing addition of two 4-bit numbers when there is no carry propagation from one stage to other stage. So that is called best case. Just like you are adding two numbers like 1000, okay, this is A number, B number I am considering like this. 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1. Here I haven't, carry has not propagated. Whatever the first stage full adder you are having, here carry input is 0. All these full adders also similar to this one, right? The moment you are giving the A and B inputs, okay, you are getting some amount of time for producing sum that is same equally for each sum bit. Similarly for carry also. Whatever the amount of time this particular full adder is taking for producing carry, the same amount of time here also will take place. So this is called best case. Best case means there is no carry propagation from one stage to another stage. This is the best case. Best case means there is no carry propagation from one stage to another stage. Next one is worst case. Here carry propagation will take place through all the stages. Suppose I am considering the number like this. A is 4 ones, B is 0001. Here 1 plus 1 is 2, sum is 0, carry is 1. 1 plus 1 is 2, sum is 0, carry is 1. 1 plus 1 is 2, sum is 0, carry is 1. 1 plus 1 is 2, sum is 0, carry is 1. Right? Here if you observe, the carry is propagating through all the stages. Okay, this is called worst case. That means this particular full adder performs the addition the moment you are giving A0, B0 because Cin is 0. Okay, here it is taking some amount of time for producing sum and similarly for carry. Now, here carry is generating, right? So this particular full adder has to wait till this carry come. Then only whatever here we are getting sum output and carry output, that will be valid. Similarly, this particular full adder has to wait till this carry come, like that. Similarly, this particular full adder has to wait till this carry come. So this is called worst case. Worst case means carry propagation takes place through all the stages. Best case means there is no carry propagation through any stage. Write on the question. A 1-bit full adder takes 20 nanoseconds for generating Cout and 40 nanoseconds for generating sum. Full stop. Find the worst case delay of 4-bit binary adder, which is formed by cascading 4 such full adders. So that means whatever the structure we have considered, this is the 4-bit binary adder. Here we have cascaded 4 full adders. Okay. Here he has given the information about one particular full adder, that is at the first stage. Okay. Whatever the information he has given, that is related to the first stage. Okay. Here Cin is 0. The moment you are giving the A and B inputs for producing sum, here in this case he has mentioned 40 nanoseconds. For generating carry, he has mentioned it as 20 nanoseconds. Now he is asking, he has cascaded 4 such full adders. Now it is becoming a 4-bit binary adder. Find the worst case delay. Worst case delay means carry propagation takes place through all the stages. Okay. First I will write whatever the sum time he has mentioned. Okay. I will place for each full adder. Here 40 nanoseconds. Okay. Similarly I will write carry. Carry is taking 20 nanoseconds. See, if the question is say best case, he never asked for best case. Okay. Suppose if it is a best case. Best case means what? Carry propagation won't take place through any stage. Okay. So that means here if you observe whatever the internal circuit diagram you are having, okay, the same circuit diagram is there in each full adder, right? So the moment you are giving the inputs, okay. So here for producing sum it is taking 40 nanoseconds. For producing carry it is taking 20 nanoseconds. Similarly the case for each full adder, right? So among these two, whichever is the larger, here it is 40 nanosecond. So that means for best case, the moment you are giving the A and B inputs, okay, in order to get the valid output is 40 nanoseconds. Because each full adder is performing parallelly, right? So if it is the best case, answer is 40 nanoseconds. Among these two, whichever is the larger, that will be the answer. Okay, now in this question he has mentioned for worst case. Worst case means carry propagation will take place through all the stages. Yeah, we can give the inputs parallelly at the same time. That's why I have given the word parallel binary, 4-bit parallel binary, because we are giving the inputs of A and B parallelly. At the same time we can give. Now the question is for worst case. That means carry has to propagate through all the stages. Okay, now see this particular full adder, initial carry is 0, right? So for producing sum it takes 40, for producing carry it takes 20. Now here if the carry is generated, that means this particular full adder is getting carry at 20 nanosecond, right? So that means this particular full adder has to start the addition operation after getting this carry. That means this time I will add here. See, till this carry come, it has to wait, right? So that means I will consider this particular amount of time. So I will add this one. 40 plus 20 is 60. 20 plus 20 is 40. Is it clear? Worst case means carry has to propagate through all the stages. Here, this particular full adder, if it is generating carry, okay, for getting carry, it requires 20 nanoseconds. So, after getting this particular carry, then only this particular full adder has to perform the addition. So, that means I am considering that. Okay. Similarly, here, this particular full adder has to perform the addition after getting this carry. This carry is coming at 40. So, I will add 40. So, 40 plus 40 is 80. Here 20 plus 40 is 60. Now, similarly, this particular full adder has to perform the addition when after getting this carry. This carry is coming at 60 nanoseconds. So I will consider that one. 40 plus 60 is 100. Here it is 80. How C2 is 40? See, this particular full adder has to perform the addition after getting this carry. Okay, this carry is coming at 20 nanoseconds. Okay, so we have to consider that particular carry, right? So for this particular full adder, individually for some it requires 40 nanoseconds only, but after getting this carry, we have to perform the addition. So that's why I'm considering 40 plus 20 is 60. Similarly for carry, individually it requires 20 nanoseconds, but this particular full adder has to perform the addition after getting this carry only, right? So this carry is coming at 20, so I am considering that particular delay. So here if you observe, in general, for all these type of questions, see, for a particular full adder, he has given 40 nanosecond and 20 nanosecond, right? For some, it is 40 nanosecond, for carry 20 nanosecond. In this case, this is greater. 40 nanosecond is the greater. So obviously, when you found out here, last stage, okay, the time required for producing sum will be larger when compared to the time required for producing carry. So at the last stage, we got here 80 nanosecond, here we got 100 nanosecond. Among these two, 100 nanoseconds is the maximum. So that is the worst case delay of this particular 4-bit binary adder. Okay. So suppose if TC, say for example, carry time is greater than some time, okay, then obviously at the last stage also this time will be more when compared to this one. Here, answer is 100 nanoseconds. That means, see, the moment you are giving the inputs, you will get some output here, but that may be a valid one or may not be valid one. But if you wait for 100 nanoseconds, so whatever the answer you are getting, that will be the value, like that. That is the meaning. Okay, this is for 4-bit case. So here we have cascaded 4 full adders. See, best case means what? There is no carry propagation through any stage. That means here Cin is 0, here also 0, here also 0, here also 0, right? So you are giving the inputs parallelly at the same time. Okay, for producing sum, it requires 40 nanoseconds. For producing carry, 20 nanoseconds. Each full adder internally, whatever the circuit diagram, you are having the same hardware circuit. Okay, since Cin value is 0, it no need to wait for the carry, right? So that means each full adder for producing sum 40 nanoseconds only. Similarly for carry 20 nanoseconds only, right? So among these two, whichever is the larger, that is the best case. That means 40 nanosecond delay. For best case, it will be 40 nanosecond delay. Best case means there is no carry propagation through any stage. After 40 nanoseconds, whatever the answer you are getting, that is the valid one. Worst case delay means carry propagation takes place through all the stages. See, I have already repeated. See, each full adder, whatever the circuit diagram, previously we have considered the same hardware circuit is there. Okay, each full adder individually perform parallelly. Okay, so here best case means there is no carry propagation. That means Cin value is 0, C1 value is 0, C2 value is 0, C3 value is 0. The moment you are giving the AB inputs, for producing some bit, each full adder requires 40 nanoseconds only. Similarly for producing carry, 20 nanoseconds only. So among these two, whichever is the larger, that will be the answer. Best case means there is no carry propagation through any stage. Worst case means carry propagation will take place through all the stages. Okay, so this is about 4-bit binary adder. Next one, 8-bit binary adder. Okay, before discussing about 8-bit binary adder, see here we have considered for 4-bit case. Okay, we have analyzed like this. Okay, if the similar question for 8-bit adder or 16-bit adder, then what you have to do? You have to continue this process till last stage, right? So, but it will take more time in the exam, right? So, for that I will give the shortcut method. I will give the generalized equation formula. See here, for producing sum, it requires Ts time. For producing carry, Tc for a particular full adder. Okay. So here, this is Ts, this is Tc. Now what I have done here, this is Ts, 16 nanosecond is nothing but Ts plus Tc. Here Tc plus Tc, that is 2Tc. See, for a particular full adder, the amount of time required for producing some bit I am assuming as Ts. Okay, for producing carry it is Tc. Okay, now for this particular full adder, what I have done, I have added Ts with Tc. Ts is the time required for producing this sum bit. Okay, after getting this carry only, I have added. So that means Ts plus Tc. Similarly, here Tc is the time required for this one. I am adding this TC, 2TC. Similarly here, for producing some TS plus 2TC. Similarly here 3TC. This one will be TS plus 3TC. Last one is 4TC. See, whatever the full adder circuit we have considered, all those are what? Combination. Combination circuit means what? You are having logic gates. The moment you are giving the inputs, okay, you will get some particular output. That may be valid or may not be valid based upon the case you are considering. Otherwise, the moment you are giving the inputs, okay, you will get the output based on the delay, whatever the amount of time it will take. Okay, so for producing, just go through the previous circuit. For full adder, you are having two exclusive OR gates. From the input side, you are having AB inputs and carry input. Okay, the moment carry input is 0, each full adder becomes half adder only. Right? So whatever the time required for producing sum, the same amount of time will be there. Similarly for carry also. If it is the best case means, for each full adder, carry input is 0 only. Even here also, for other case, for worst case also, see, each full adder may perform parallelly the operation, but unless otherwise this particular carry is considering, whatever the output here I am getting, that may be valid or may not be valid. But if I wait till this carry come, then after that, say after 16 nanoseconds, whatever the output here it is there, that is the valid. I will consider like that. That is the meaning. Otherwise, the moment you are giving the inputs, you are getting some particular output that may be valid or may not be valid based upon the delay and based upon the carry. Whether carry is generating from one stage to other stage like that. If carry is generating from one stage to other stage, then that particular full adder has to consider that particular carry. So after getting that carry, it will produce the sum. So here, this particular full adder after 60 nanoseconds, whatever the output is there, that is valid. Similarly for this particular full adder after 80 nanoseconds, whatever the output is there, that is valid. Similarly for this full adder after 100 nanoseconds, whatever the output is there, that is valid, like that. Otherwise, the moment you are giving the A and B inputs, after 40 nanoseconds, you will get some output here that may be valid or may not be valid. That's what I am saying. Okay. So here, if you observe, okay, you can write this is the first stage, second stage, third stage, fourth stage. Okay. At fourth stage, I am having 4 times TC. Third stage, 3 times TC. Second stage, 2 times. First stage, 1 time. Okay. For generalized case, at last stage, we can write the amount of time required for producing carry at the last stage. You can write down the time required for producing the C out at nth stage full adder is equal to N into TC. N into TC. See here, for 4-bit case, we have considered 4 full adders. That means at last stage means N value is 4. If it is 8-bit case, N value will be 8, like that. Here TC is the time required for producing carry out or C out of a full adder. Next, regarding sum, here 4th stage, but I am having 3 here. So this one I can write it as TS plus 4 minus 1 into TC. Okay. Third stage, I am having 2. This one I can write it as TS plus 3 minus 1 into TC. Next, second stage, here I am having 1. This one I will write it as TS plus 2 minus 1 into TC. Similarly, this one I will write it as TS plus 1 minus 1 into TC. If it is the first stage, 1 minus 1. Second stage, 2 minus 1. Third stage, 3 minus 1. Fourth stage, 4 minus 1. Like that, for generalized case, we can write. Write down the time required for producing the sum bit at nth stage full adder is equal to TS plus N minus 1 into TC. For 4th stage, we got TS plus 4 minus 1 into TC. For nth stage, it will be TS plus N minus 1 into TC. So here TC is the time required for producing carry of a full adder, and TS is the time required for producing the sum of a full adder. He will give the information about TS and TC. Okay, if it is a 4-bit case, substitute N value 4. If it is a 8-bit case, substitute N value 8. So here, after substituting these two values, whichever is the larger, that will be the answer for worst case delay. Next one, 8-bit binary adder. Next one is 8-bit binary adder. So previously we have considered 4-bit binary adder. If you consider that entire 4-bit binary adder single block, okay, we can cascade 2 4-bit binary adders in order to get 8-bit binary adder. Here I am representing a strike on a single line, which indicates it is not the single line, those are parallel lines. If you want, you can write like this also. This is not a single line, those are multiple bits or multiple lines. Here when we are giving two 4-bit numbers, here the resultant sum will be 5 bits, among which 4 are the sum bits and C4 will be the carry output or MSB. Okay, that one we will give as a carry input for this particular binary adder. So here we have cascaded two 4-bit binary adders in order to get 8-bit binary adder. Here if you observe, the carry output of this one we are giving as carry input for this particular binary adder. Previously, if you remember, for implementing a 4-bit binary adder, we require only 3 full adders and 1 half adder. But for uniformity, I have considered 4 full adders because the reason is this one. In general, we will be having 4-bit binary adders like one IC package. Okay, whenever we want to implement higher order binary adders, there what we can do, the carry output of this one we will give as carry input for this. Okay, if you are using first stage half adder, there you will be having only 2 inputs. You don't have another input for giving this carry, right? So that's why I have used 4 full adders. See, if it is at the first stage 4-bit binary adder, always carry input will be 0. If we are using at the second stage or third stage or fourth stage, then what will happen? The carry output of previous one will be the carry input for current state, like that. So there, if we are getting carry input as 1, okay, so we have to give that one as the input. So that's why I am using 4 full adders. Okay, you can make a note. By cascading two 4-bit binary adders, we will get 8-bit binary adder. Next point. Similarly, by cascading 4 4-bit binary adders, we will get 16-bit binary adder. That is the advantage of 4-bit binary adder, or you can say full adders cascading. Okay. See, previously we have implemented half adder with the help of truth table. Similarly, full adder with the help of truth table. Whereas for 4-bit binary adders, I haven't used any truth table concept. Just by cascading 4 full adders, I got 4-bit binary adder. Actually, if you want to formulate the truth table, then here say for example 8 bits, 4 bits you are having, here 4 bits, total 8 bits. Of course, C input is 0, that means 2 power 8, 256 combination of zeros and ones will be there, and for each combination of input you have to find out what is the output, what is the sum value, what is the carry value, like that. But the advantage of cascading, because of that one only, we have implemented 4-bit binary adders just by cascading 4 full adders. See, previous case we got say 100 nanoseconds. See, when compared to 1 second, 100 nanosecond is nothing, right? So that's why when we are giving the inputs, whatever the output we are getting, that is the like when we are seeing, okay? So whatever the answer, it is already there, that is the valid one. Nano means 10 power minus 10. 100 into 10 power minus 10 is 10 power minus 7. In 1 second, 10 power 7th part. Write down the question. You can use these formulas in order to solve this particular question. Write down the question. In an 8-bit binary adder, the first stage full adder takes 32 nanoseconds for generating sum and 24 nanoseconds for generating C out. And among these two, whichever is the larger, that will be the answer. Here in this case, n value is 8. See here, the time required for producing sum is 32 nanoseconds. Here he has given 32 nanoseconds is TS, and for producing carry, that is TC, 24 nanoseconds. Here in this case, n value is 8. N value is 8. Substitute these values here. Among these two, whichever is the larger, that will be the answer. Yeah, 200 nanoseconds is the correct answer. Substitute here. First let us see for C out. For C out, formula is n into TC. Here n value is 8. TC value is 24. 192 nanoseconds. For generating carry at 8th stage, it will be 192 nanoseconds. Now let us see for sum. Formula is TS plus n minus 1 into TC. Here TS is 32 nanoseconds plus n value is 8. 8 minus 1 into TC, 24. 7 into 24 will get 200 nanoseconds. Okay, so among these two, whichever is the larger, that will be the worst case delay. Okay, see in general, for this type of questions, the very clue point is, he will give the information about a particular full adder. Okay, if, see in this case, TS is greater than TC, right? So you no need to find out both of these. You just find out this one only. See, the moment for a first stage full adder, if TS is greater than TC, obviously at the last stage also, for producing the sum will take more time. So you no need to calculate this one. Okay, suppose if we give, say TC is greater than TC, right? So you just find out here only. You don't need to calculate this one. If both are same, then you can use either of the formula. See here, just substitute if both Ts and Tc are same. Here what will happen? N minus 1 into Tc. Okay, here minus Ts plus Ts will get cancelled. N times Ts you will get. So here N times Tc, both are same. If Ts and Tc both are same, then you can use this formula or this formula, both will give the same answer. If Ts is greater than Tc, then you just find out this value. Okay, that will be the worst case delay. If Tc is greater than Ts, then you find out this value. That will be the greater or worst case delay, like that. See, worst case delay means what? We are finding the carry is propagating through all the stages. At the last stage, we are finding for producing sum and for producing carry, what is the amount of time. Okay, among those two, whichever is the larger, that will be the worst case delay. So for first stage, if Ts is greater than, then obviously at last stage also Ts only will take more time. You can observe the previous question and this question. In both the cases, I have considered Ts value is greater than Tc. Now I will consider one more question where both are same. So you can use either of the formula, you will get the same answer. Yeah, for best case, whatever he has given information about a particular full adder, right? Ts, Tc. Among these two, whichever is the greater, that will be the answer for best case. Suppose in this case, 32 nanoseconds will be the answer for best case. Okay, fine. Write down the question. The propagation delay of an exclusive OR gate is twice that of an AND gate / OR gate. That means for AND gate and OR gate, you are having one propagation delay, it is same. Okay, the propagation delay of XOR gate is twice that of this one. Okay, full stop. The propagation delay of an AND gate / OR gate is equal to 1.2 microseconds. This is the question asked for gate CSE branch. Just look at the previous questions and this question. Just go through the question. What data he has given earlier questions. Here what data he has given. Just try to observe. In the previous questions he has given the time required for producing sum and time required for producing carry output of a particular full adder. Okay. But in this question he has not given that particular information. But he has given information about exclusive OR gate, AND gate, OR gate. Okay. So whatever the explanation we have given, we have discussed earlier regarding a particular full adder. Inside full adder you are having two half adders and OR gate, right? In each half adder you are having exclusive OR gate, AND gate, like that, right? So he has given the information about everything in the question. Since we know, I have skipped that part. Okay. But here if you observe, he has given information about gates. That means he went inside the circuit. Inside full adder you are having half adder and OR gate. Two half adders, OR gate. In each half adder you are having exclusive OR gate, AND gate. Okay. Now he has given information about exclusive OR gate, AND gate, how much time it is taking. Okay. From this information, if we can able to calculate what is Ts, what is Tc. Okay. The moment if you get Ts and Tc, after that you can substitute those values here. Here it is for 4-bit case, you can substitute n value 4. Okay. Now let us solve. Draw the circuit diagram of full adder, not 4-bit binary adder. Draw the circuit diagram of full adder. This is the circuit diagram of full adder, right? So we are having two exclusive OR gates, two AND gates, OR gate. Okay. Now he has given the information about AND gate and OR gate. How much time it is taking for AND gate or OR gate? 1.2 microseconds. For AND gate or OR gate, the propagation delay is 1.2 microseconds. And he has given the relation between exclusive OR gate and AND gate or OR gate. The propagation delay of exclusive OR gate is twice that of AND gate or OR gate. That means multiply with 2. 2 into 1.2. That is 2.4 microseconds. That means exclusive OR gate is taking 2.4 microseconds, whereas AND gate and OR gate is taking 1.2 microseconds. Is it clear up to now? Based on the given data, I have written. Here we are giving the AB inputs directly, right? But this particular exclusive OR gate is taking 2.4 microseconds. This output will be available at 2.4 microseconds. Okay, exclusive OR gate is taking 2.4 microseconds. So after giving the inputs, here in order to get the output, it requires 2.4 microseconds. Now, other input, Cin we are directly giving. That means there is no delay here. You can say 0 microsecond. Okay. So here our intention is what? Worst case delay or maximum propagation time. So here for this particular exclusive OR gate, okay, we are having two inputs, among which this input I am getting directly. Now you can observe from this particular question, whatever the doubts you are having till now, all those doubts will be clarified through this question. Okay, see here, A, B are direct inputs, similarly C is also direct input. So here we don't have any delay. Okay, now this input is directly coming, but whereas other input for this exclusive OR gate, I am getting a 2.4 microsecond delay, right? So among these two, which I have to consider? How much time for this particular exclusive OR gate has to wait? 2.4 microseconds, right? Okay. So now this particular exclusive OR gate is already having same 2.4 microsecond delay. So this output will be valid. Okay. If I consider this particular delay, right? So 2.4 plus 2.4, that is 4.8 microseconds. Is it clear? See, this particular exclusive OR gate require 2.4. Similarly, this exclusive OR gate also require 2.4. Okay, I have given direct inputs. I am getting the output at 2.4 microsecond. Now, other input I am getting at 0 microsecond only. But among these two, this is taking some time. So I have to consider this particular amount of time. Okay, so here output will be available at 2.4 microsecond plus 2.4 microsecond. That means at 4.8 microsecond, whatever the output here I am getting, that is the value. So that means this is the amount of time. 4.8 microsecond is the amount of time required for producing some bit of a full adder, that is TS. Okay, fine. Now, let us look at regarding carry path. See, carry is requires 1.2 microsecond. Sorry, for AND gate it is taking 1.2 microsecond. Here also AND gate requires 1.2 microsecond. OR gate also same, 1.2 microsecond. Here inputs are direct inputs AB. Okay, so those are coming directly, right? But this output will be, we are getting after this delay, 1.2 microsecond. 1.2 microsecond. See here, this particular AND gate having two inputs, among which one input is seen, that is the direct input 0 microsecond only. Other input is what? Output of this exclusive OR gate, that is coming at 2.4 microseconds. So I have to consider the same amount of time. See here I have to consider this 2.4 microsecond. Is it clear? See, one of the input I am getting at 2.4 microsecond, other input I am getting directly 0 microsecond. So among these two, whichever is the largest, that one I will consider. This AND gate output will be active or valid if I consider these two delays, 2.4 plus 1.2, that is 3.6 microseconds. Up to here, is it clear? 3.6 microseconds. Okay, fine. Now, just observe this particular AND gate, sorry, OR gate, this particular OR gate having two inputs. Okay, one input is coming at 3.6 microsecond, but other input is getting at 1.2 microsecond. So, which one I have to consider? 3.6. I have to consider 3.6, right? So, this output will be 3.6 plus 1.2, that is 4.8 microseconds. So, that means this is 4.8 microsecond is nothing but carry, the time required for producing carry, TC. So, the moment you give the inputs AB and C in, okay, in order to produce sum, it is taking 4.8 microseconds. Similarly, for producing carry, it is taking 4.8 microseconds. In this case, both TS and TC both are same. You can use either of the formula, both will give the same answer. Here, N value is 4, TS value is 4.8. Okay, you can substitute either of the formula, you will get the same answer. Yes, 19.2. Correct. See here, we are given the inputs. Okay, if you observe the inputs to some output, you are having two stages. Okay, and for carry, you are having 3 stages. Okay, based on the propagation path from input to output, okay, the propagation delay will vary. From the input to output, based on the propagation path, the propagation delay will vary. Okay, I am quickly repeating once again, just go through. Here he has given the information about AND gate or OR gate propagation delay is 1.2 microsecond. Whereas for exclusive OR gate, he has mentioned 2 times that of AND gate or OR gate. That means 2 into 1.2 is 2.4 microsecond. Now, so here exclusive OR gate requires 2.4. Here also it requires 2.4 microsecond. So that means the output of this one is available at 2.4 microsecond. For this exclusive OR gate, I am getting seen as the one of the input. That is coming direct input. That means there is no delay. But whereas for other input, I am getting a 2.4. So among these two, whichever is the larger, that one I will consider. Okay. So here output will be valid when you consider this particular delay. So 2.4 plus 2.4, that is 4.8 microsecond. Similarly, regarding carry, let us find out the time. Here both the inputs are coming directly, right? So the output of this AND gate will be valid at 1.2 microsecond. Similarly here, this AND gate requires 1.2 microsecond, but here the inputs are, one input is direct input, another input is output of this exclusive OR gate. This one is available at 2.4, so I will consider this one. Now, the output will be available at 2.4 plus 1.2, that is 3.6 microsecond. Now, this particular OR gate also requires 1.2 microsecond, but the inputs are, here it is available at 3.6, here it is available at 1.2. So, among these two, whichever is the larger, that one I will consider. 3.6 plus 1.2, that is 4.8. Okay, so in this case, we got both TS and TCR, same 4.8 microsecond. This particular question is related to 4-bit binary adder. So, you can consider n value 4. Okay, you can use either this formula or this formula, both will give the same answer. Because TS and TCR same, 19.2 microsecond. Right. So, up to now, we have discussed about binary adders. Like we started with 1-bit binary adder, that is half adder. Then we started full adder, and then 4-bit binary adder, like that. Like that, we have implemented higher order binary adders. Okay. When you consider half adder, there you have considered the carry. Okay. Similarly, you will be having half subtractor, full subtractor, and then 4-bit binary subtractor, like that. Okay. There you require difference and borrow. Here we have considered sum and carry. There you have to consider difference and borrow. Okay. Similarly, you can try for those subtractor later.